All right, one quick definition here, and then let's find extreme values. So my definition is this definition. A critical number of a function, a critical number of f of x is a value, let's call it c, such that f prime of c equals 0 or f prime of c does not exist. So it's a place where the derivative is 0 or where the derivative doesn't exist. Now the derivative doesn't exist for several reasons. You might have a sharp corner, you might have a vertical tangent line, right? Y equals x cubed, for instance. There's nothing that goes wrong with the function itself there, but the tangent line is vertical, and so the slope of that tangent line is undefined. Anyway, that's one way. You could have a sharp corner. That's another way that the derivative might not exist. So any value, so this is an x value. The critical number is an x value where either the derivative is 0 or the derivative doesn't exist. Okay. And the theorem that we want to work with here is that says that f of x has extreme values actually, if f of x has an extreme value, so either a max or a min, then it happens at, a critical point, at a critical number, or at an endpoint of the domain. So when I'm looking for critical values, I need to look in 3 places. I need to look at endpoints, and I need to look at critical points. That sounds like 2 places, but there's 2 types of critical points. Okay. For example, here's a function. F of x equals, let's do x cubed minus 9x squared plus 24x plus 7. All right, and I'm going to give you on the interval from 0 to 5. Let's find all the maxes and mins, all the local and global. So what are the words? Relative and absolute. Again, I'm not sure which words to use. But what I'm going to do is I'm going to find all the local maxes and mins and the endpoints, and then see which ones are the absolutes. Because I have a closed interval of finite length, and I've got a continuous function, right? This is a polynomial, so it's continuous. A theorem we had from one of the videos previously says that there has to be a maximum and a minimum. Okay, those maximum minimums have to happen at extreme values, sorry, at critical values, or at endpoints. So to find the critical values, I need to take the derivative and see when it's not defined and see when it's equal to 0. So here we go. Take the derivative. 3x squared minus 18x plus 24. Well, that's a quadratic function. That's always defined. So I'm not going to have critical values where the derivative is not defined. I'm only going to have critical values when the derivative is equal to 0. So critical value when this thing is equal to 0. When 0 is equal to 3x squared minus 18x plus 24. I could use not Pythagoras, I could use the quadratic formula, but I think I can actually just factor that. If I see a 3x squared minus 6x plus 8, right? And then, so I've got 0 equals 3 times, and I think this factors into x minus 4 and x minus 2. Yeah. So x equals 2 or x equals 4. This is a cubic polynomial. You got any idea what the graph of it looks like? Right? In general, cubic polynomials look either like this or like that. With a positive coefficient in front of the x cubed, it looks like this. So just from that knowledge already, the x equals 2 and x equals 4, I'm thinking, well, this one must be the 2 to be a local maximum, and that one must be the 4 to be the local minimum. Okay? I'm all in favor of using that kind of reasoning. You know information about polynomials. Now I know exactly where that high point and that low point are. I don't have to guess. I mean, derivative 0 could be either max or min, but I use a little bit more knowledge of the function to tell me which one's which. But those are the two critical values. There's also two endpoints. So what I'm going to do is I'm going to look at four things. I'm going to look at the function value at my left-hand endpoint, the function value at my first critical point, the function value at my second critical point, and the function value at the last endpoint there, so x equals at 5. So I'm just going to plug them in to the original function, and what was the function here? It's that. So I'm going to have 0 cubed minus 9 times 0 squared plus 24 times 0 plus 7, which is 7. That one's easy enough. Plug a 2 in, so 2 cubed minus 9 times 2 squared plus 24 times 2 plus 7. So I've got 8. What is that equal to? Equals 27. And then I'm going to do 4 cubed minus 9 times 4 squared plus 24 times 4 plus 7. And that's equal to 23. And lastly, I've got 5 cubed minus 9 times 5 squared plus 24 times 5 plus 7, which is equal to, it's equal to 27. So what do I see here? What do I see? I see the absolute min of 7 at x equals 0. I have an absolute max of 27 at actually two different places, right? I have it at x equals 2 and x equals 5. That's okay. You can have the absolute max in several places. And this 23 must be a local min of 23 at x equals 4, right? Notice how I distinguish between the function value, the maximum or minimum function value, and where it happens. All right, I think we need to do another example, but let's do it in the next video.